When I say engineering, what pops into your head? Probably things like steel beams, aluminum frames, iron, strong, sturdy metals. But what if I told you that some of the most critical materials in engineering aren't metals at all? We're going to dive into this surprising world that's pretty much hiding in plain sight.
Okay, let's start with a little riddle for you. What does a classic old-school radio, the tires on your car, and the outlet on your wall all have in common? And no, the answer's not metal. The answer is this powerful and incredibly versatile family of non-metallic engineering materials.
So you have to wonder, why would an engineer ever pick something that isn't metal for a job? Well, it turns out there are some really good reasons, and they might not be what you think.
It really boils down to this incredible combination of properties. A lot of the time, non-metals are cheaper, they're way more flexible, and, this is a big one, they are terrible at conducting heat and electricity. So for some jobs, they're not just a nice-to-have, they're literally the only thing that will work.
All right, before we jump into all the cool, modern, lab-grown stuff, let's take a step back. Let's start with the original engineering non-metals, the materials we've been using for centuries, pulled straight from nature's own toolbox.
So this table right here, it's a perfect little snapshot. You've got timber, leather, and rubber. Each one is a superstar in its own right for a specific reason. Timber is a fantastic insulator. Leather can take a real beating. And rubber? It's the undisputed champion of soaking up vibrations. Let's dig into each one just a little bit more.
First up, timber. You see, its big superpower in engineering is that it's just terrible at conducting heat and electricity. And that's exactly why it's perfect for something like a foundry pattern, where you're pouring molten metal, or even for really specialized things like bearings that are lubricated by water.
Next up, leather. I mean, think about it. It's super tough, but it's also flexible, and it can take a real beating without wearing out. That's the perfect recipe for parts that are always moving and rubbing against each other, like the big belt drives you'd see in old factories, or even just simple, reliable washers.
And of course, rubber. Now, rubber has something called a high bulk modulus. It's a fancy term, but all it really means is that rubber does not like to be squished. And that resistance to being compressed is exactly what you want for making tight seals in an engine or for stopping a machine from rattling itself to pieces. It keeps things quiet and sealed up tight.
Okay, so those are the OGs, the classics from Mother Nature. But the real revolution, the thing that changed everything, that happened in a lab. And this, my friends, is where plastics enter the scene.
Plastics were a total game changer. Fundamentally, they're synthetic materials that we can mold into pretty much any shape you can dream up. On top of that, they don't corrode, they hold their shape really well, and they're relatively cheap to make. For a designer, this was a dream come true. But here's the kicker, the part that's kind of mind-blowing. For all the thousands and thousands of different plastic things you see every single day, they all boil down to just two fundamental categories. That's it. So what's the big difference? It all hinges on one simple question. When you heat it up, does it melt so you can use it again? Or does it set, like, forever? This is the great divide in the world of plastic. The secret sauce here is a chemical process called polymerization. The best way to think about it is like this. Imagine you have a giant box of tiny molecules, like individual Lego bricks. Polymerization is the process of snapping all those bricks together to form these super long, strong chains. And here's the important part. Once that structure is built, it's permanent. This one little process, it's the key to everything.
Okay, if you remember one thing, make it this analogy. It's the absolute best way to get it. Thermosetting plastics. They're like a cake. You mix the batter, you bake it, a chemical reaction happens, and poof, you have a cake. You can't unbake it and turn it back into batter, right? Now, thermoplastics, they're like a chocolate bar. You can melt it, pour it into a new shape, let it cool, and guess what? You can melt it and do it all over again. No permanent change.
This quote just nails it for thermosetting plastics. That chemical change, that polymerization, it's a one-way street. Once it's baked, you cannot turn it back into batter. Once it's set for good. So where do you see these set-it-and-forget-it plastics? Well, think of bakelite, that classic heavy material from old radios or the handles on your pots and pans. It's super tough and heat-resistant precisely because it went through that one-way chemical change. The epoxy glue you might have at home? Same deal. And then you've got the other side of the coin, the shapeshifters, the thermoplastics. Honestly, these are the ones you probably run into all the time. We're talking about the polythene in plastic bags or the PVC used for pipes. The key is they just soften when they get hot and get hard when they cool down, over and over again. No chemical drama, which means, yep, you can melt them down and remold them.
All right, so we've got our two teams, the ones that set forever and the ones that can be remelted. Let's pull the camera back a bit and think about what this actually means for, well, for everything we build around us. It really is this simple. One type can be remelted and reshaped, and the other cannot. And that single difference, as small as it sounds, changes absolutely everything. It affects how we manufacture things, how we design them, and, yeah, how we deal with them when we're done. And that really leads us to the big final question, doesn't it? In a world that's more and more focused on things like recycling and sustainability, what does this difference really mean for our future? Knowing that one family of plastics is way easier to recycle than the other, how should that change what we make and how we make it? The whole conversation really starts right here, with understanding these materials from the molecule up.